Hi, this is Robert Owen. Thanks for coming back and watching part 6 of my series on introducing digital command and control for model trains. In part 6, I want to explain the use of the LN298N motor driver. In previous videos in this series, I explained how DCC worked, how the Uno could be used to implement DCC. But in particular, I explained how to use the R3 motor shield to implement DCC. In this video, I want to explain how to use the LN298N H-bridge as an alternative. The top left up here is the Uno, which is common for both DCC if I implement with the R3 motor shield, or if I implement it with the LN298 motor driver board on the bottom right. The difference between the 298 and the R3 motor shield is that there's some slight changes to the software run on the Uno, but in particular, the 298 is a standalone board that needs to be separately wired to the Uno, quite unlike the R3 motor shield, which plugs directly on top of the Uno. First though, a brief recap of the Uno and the motor shield. The way I implemented the DCC script on Uno, the output from pin 3 on the Uno into the motor shield was a permanent logical high at plus 5 volts. The input into pin 12 alternated between logical 0 and logical 1, between 0 volts and plus 5 volts. And this resulted in the output from the connector at the edge of the R3 motor shield connecting to the track, and from there on to the decoder, varying between minus 10 volts and plus 10 volts, as required by DCC. So the only thing left to do was to vary the width of this pulse between 57 microseconds and 100 microseconds, depending on whether I want the DCC data on the track to be logical zeros or logical ones. Let's look at more detail in the 298. There are two sets of input power to the 298. The bottom left-hand connectors here are the main high power input power to power the train or the motor using the 298. So these two connectors A and B on the right and left connect to the railway track or to a robot, and the power coming in here in the two bottom left connectors is the main power supply to power either the train or the robot. Now, if we put DC into these bottom left two connectors, the plus wire connects to the left and the negative wire connects to the central connector. There's a 2 volt drop across the board, so if you put 12 volts into here, you get 10 volts out of either A or out of B. So it's important to know how many volts you want out of these connectors, and you add an extra 2 volts into the input in the bottom here. Now, the motor shield, or the LN298N, needs a common ground with the Uno. So the negative input for power to the 298 needs to be also be connected to the ground pin on the Uno. That grounds them together and gives a common ground. Now, even though we provide DC, say 12 volts into these two connectors here, we don't want steady power out of A or B. We want either DCC signals or pulse width modulation power signals. And we do that by controlling the input to the 3 pins here A, or the 3 pins on the left B. 3 pins on the right A control the output power from A, and the 3 pins little b on the left control the output power from pin B, as I'll explain later. Now, before we move on, if you look closely at the 298, there are 3 jumpers on it, A, B, and C. And the way we implement DCC, it's important that you remove jumper A. It's taken out altogether with tweezers or with fingers, but we leave in jumpers B and C. Why do we take out jumper A? There are 2 requirements of power on this board. We need to insert power into connector D so that we get power out of these 2 connectors here to power the train, and power out of these 2 connectors on the left also to power another truck or a train or a robot. So theoretically, the power in here could also power the digital logic on the board. But if the input power here into D to power the train is say 12 or 14 volts, it is quite likely to be too high a voltage for the digital logic here. It will blow the logic. So we want to tell the board that even though we're providing 12 volts power into D, we don't want this power to power the digital logic on the board. We only want it to control the 298 in here. So the way we tell the board not to take power off here to control this circuit in the middle here is by removing this jumper. So the power in here goes directly to the 298 attached to the heat shield here, and from there out of these 2 connectors here. So how do we power the digital circuit on the board? This rightmost connector on the bottom, we connect to +5 volts on the Uno or some other supply of +5 volts. The negative from the Uno comes as the common ground into the central connector here. Yes, so that tells the board that power for the board comes in here from the Uno, power for the 2 connectors for the train comes into D here by removing this jumper. What are jumpers B and C for? Jumper B is associated with these 2 connectors, and jumper C is connected with these 2 jumpers. We'll go into this in a bit more detail later, but by leaving jumper B installed or inserted, we're telling the 298 that out of these 2 connectors on the right, we do not want pulse width modulation power. We want digital DCC signals sent to the decoder on the train, and it'll be the decoder that will generate the pulse width modulation power. If we were to remove this jumper, effectively we'll be allowing the 298 to generate its own pulse width modulation power out of B, which is what we don't want. And jumper C and these other 2 pins next to it control the output power in a similar way from the connector on the left. More on wiring up the 298. We have the Uno on the left, the 298 on the right. Plus 5 to 35 volts power goes into these top 2 connectors, positive on the top, negative on the bottom. If you're just controlling a relay or a motor on a robot, you can use anywhere between 5 and 35 volts. Because we're implementing DCC, this voltage must be 10, 12, 14 volts or the engine won't work. The middle connector also acts as a ground, a common ground between the 298 and the Uno. There's a wire also going into ground on the Uno. And 5 volts to power the 298 comes from the Uno, and this is connected to the 5 volts output on the Uno. The digital signals from the Uno, which tells connector A whether you want logical zeros or logical ones for DCC, come in from pins 11 and 12 onto these two connectors here, and this jumper is left connected for connector A. This jumper is left connected for the top jumper, and these two pins here control the digital output or pulse width modulation output from the top connector. In more detail now, the signals going in. I mentioned these bottom two connectors are plus and minus 5 to 35 volts power directly for the motor or engine. The middle connectors are common ground to the Uno, and the top connector is plus 5 volts from the Uno or some other source to power this digital logic here. The output from the 298 goes to the track from its top connector A. We want either minus 10 volts or plus 10 volts out to connector A. If into pin 12 you put a logical 1 or 5 volts, into pin 11 you put logical 0 or 0 volts at the same time, the output from the connector A will be minus 10 volts. If into pin 12 you put logical 0 or 0 volts, and into pin 11 we put logical 1 or 5 volts, out of the top connector comes plus 10 volts. So by alternately modulating or putting alternate digital signals into pin 11 and 12, the way I've implemented my script and circuit, we can get plus and minus 10 volt digital data out of connector A. So the only thing left to do now is to vary the width of this pulse into 57 microseconds or 100 microseconds, depending on if we want to output DCC logical 0 or DCC logical 1. So how does the LN298N work? Essentially, the board performs two functions. One, it controls the direction of the motor from the two side connectors. Either the motor goes forward or it goes backwards. Either in DCC we get plus 10 volts or minus 10 volts out of that. And that's controlled by what we call the H bridge. The second function it performs is to provide more power to the motor, high power to power the train, which is controlled by the H bridge. And the way this is implemented is different with DCC than if we're using the 298 to directly provide pulse width modulation power for the robot. How does the H bridge work? There's a circuit similar to this implemented on the board. There are 4 switches on it. If the leftmost switch is closed and the top rightmost switch is open, the bottom leftmost switch is open and the bottom rightmost switch is closed, power comes down, goes from left to right through the motor to earth, and the motor turns in an anti-clockwise direction, or you get, say, plus 10 volts out of the connector. If the switches are reversed, so the top left switch is open, the top right switch is closed, the bottom left switch is closed and the bottom right switch is open, the power comes in from the right to the motor and the motor turns in an anti-clockwise direction if it's a robot, or we get minus 10 volts out if it's a DCC. So it's quite a simple implementation of a H bridge. And these 4 switches here, top left, top right, and bottom left and bottom right, are controlled by these 2 pins here, input 1 and input 2 for connector A, and these 2 pins here for connector B. If into pins 1 and 2 we put low and low, the motor is turned off completely. If you put high and low, the motor goes forward, and so on. So it's quite straightforward. So pins 11 and 12 implement this forwards and backwards. Say this is 11, this is pin 12 to implement forwards and backwards. So the 298 providing DCC control signals. We have the Uno, 10 to 14 volt power for the engine. Out of pins 11 and 12 into these 2 connectors, this jumper is removed at the top, this jumper remains in. The digital signals from 11 and 12 into the 298. These are used to formulate DCC packets which are sent to the decoder on board the train. The decoder analyzes the control byte of the packet, converts it into a pulse width modulation power output to control the engine motor speed or direction. Alternatively, you could implement the packet or formulate the control byte in the packet to turn, say, the lights on or off, or to blow the whistle or blow the horn. If you're using the 298 to provide pulse width modulation power for the motor, 11 and 12 again reverses direction, but not so frequently. And into this bottom connector here, which used to have a jumper across it, the jumper is removed, and into this bottom connector now is a digital 0 and 1 to specify the pulse width or the pulse width modulation signal. And doing this, we implement pulse width modulation power directly on the 298, which is fed to the robot to power its motor without the need to use a decoder. How are the signals set up for pulse width modulation to power a robot? The jumper is removed on top. Into the top connector here where the jumper was, we are feeding logical 0 or logical 1 from the Uno. And into these 2 pins here from pin 11 and pin 12, we are either continuously transmitting a low or continuously transmitting a high for as long as we want the robot to move forward or move backwards. You can see whatever waveform we transmit from the Uno into the top connector, the same general shape comes out of these 2 connectors as a pulse width modulation signal as plus 10 volts. The width varies depending on the output power for pulse width modulation to power the motor. How do we set the motor into forward or reverse? For the same speed in forward and reverse, the digital signals into the top connector are these logical 0 and 1 pulses. If pin 11 is high and pin 12 is logical low, out of this top connector is plus 10 volts, which will move the motor forwards. If these 2 voltages are reversed, so out of pin 12 comes a logical high, out of pin 11 comes a logical low with the same shape pulse here. The pulse width modulation power out of the top connector is minus 10 volts, putting the robot into reverse. So it's slightly different to the way DCC is implemented, but they both work equally well depending on the application. So that's how the 298 hardware is implemented for DCC and how it's also used for robotics. In the next video in the series, part 7, I'll explain how I've modified the LN298N software from the Arduino R3 motor shield software to implement it for DCC. Thank you.